Hello everyone, this is Roshan. Welcome to week 9 live session. Today I will be discussing three lectures which is based on week 9. In the previous session I have conducted a live session which is based on week 8. So let's start the today session. So in week 9 we have three lectures which is on bending of beams. So lecture 23, 24 and 25 will be covered today, and in these three lectures you will be see that different concepts related to bending of beams. So let's start. So week week 9, and in this week 9 we have three lectures: bending of beams. The first two lectures is based on bending of beams, which is basically, I write it as pure bending of rectangular beams. Pure bending of rectangular beams. Next lecture is on bending of beams. So here will be also present, and the last lecture is on bending of unsymmetrical beams. Bending of unsymmetrical beams. Okay, so first of all, I will recapitulate the concepts which is already taught in these lectures. So I just give the overview of the brief overview of these three lecture, uh, and I will write some formula here which can be used in solving the problems which I will discuss later on. So in these lectures, first it start with the bending formula and the concept on neutral axis and neutral plane. So basically neutral plane is a plane where there is no bending, there is no stretching happen. This is on this plane, and the line element on the neutral plane are called neutral lines. So in bending, in the pure bending, the longitudinal strain is given by the formula which I have written here. So yeah, let's start. So longitudinal strain. In case of pure bending, in case of pure bending, we have the formula for longitudinal strain. So longitudinal strain, which is nothing but epsilon xx. Okay, if the beam axis is aligned along x direction, so the longitudinal strain is given by epsilon xx, which is given by minus y upon r, where y is the position of the position of the line element from the neutral axis. Okay, so suppose this is a cross section, suppose we have this cross section and this is a neutral axis. So the distance y is the location of point from the neutral axis, and r is the radius of curvature. Suppose we have one beam and we apply moment across its end, so it actually bend. So it actually bent, and the it actually bent and the radius of curvature. So this is basically the radius of curvature. R here is basically radius of curvature. Okay, so the longitudinal strain is given by this formula. Will be we'll use this formula while solving the problem. Okay, so this is the formula for longitudinal strain. It can also be written as in terms of other value. 1 by r is basically we say curvature. So minus y into kappa, which is also equal to minus y into kappa, where k is the curvature. Okay, and r is called as radius of curvature. So this is the formula for longitudinal strain, and the longitudinal stress is given by this formula. Longitudinal stress is given by sigma xx, which is nothing but E times epsilon xx, which is nothing but E times y upon r. So this is the formula for longitudinal stress. I hope everyone is understanding these concepts. If anyone have any doubt during the session, you can please unmute yourself and ask this question. So this is the formula for longitudinal stress. Now we also have a formula for radial or radius of curvature of neutral line. So radius of curvature of neutral line, which is given in terms of bending moment. So it is given by r is equal to EIZZ upon mz. Okay, so this is the radius of curvature formula of the neutral line, where E is the Young's modulus and I is the second moment of area and mz is the moment about z-axis. Okay, so suppose this is the beam, we have this axis beam. This is the beam, and this beam axis is along x direction, and the cross section, actually the cross section, so this is along x, this is along z direction, and this is along y direction. So moment of area about z axis, and mz is the moment about z axis, and E is the Young's modulus. Okay, so this is the formula for radius of curvature of the neutral line. We can also retain the bending moment formula using this relation, that is mz is nothing but EIZZ upon r. We can also write it as EIZZ into kappa. Okay, so this is the formula for bending moment. So using this formula, sigma xx and mz, we can derive one relation. So basically we have this one common relation, which is also known as bending equation. Sigma xx equal to minus mz y upon izz equal to minus of E into y upon r. So this is the final bending equation. This equation is also called bending equation. Okay. I hope you will be understanding these concepts. Now the next concept is IZZ, how we can calculate IZZ. So this we have a cross section, and this is our neutral axis, and this is some distance y. and suppose the height of the cross section is h and width is b. So Izz is given by integral over y dA, okay, which is also equal to integral over y dy dz, and if we integrate it from the limit, that is from minus h by 2 to h by 2, y square dy integral over minus b by 2 to b by 2 dz, which is same as, if we calculate this, we can find that Izz coming out to be 1 by 12 bh cube. So this is the formula for second moment of area. So we will be using this formula while solving our problem. Next is coming, this is the longitudinal stress and the longitudinal strain. Now we will show you the formula for the lateral strain, that is epsilon yy and epsilon zz. So we can use the strain displacement relation, which is already discussed earlier. In the previous sessions, I have shown you the formula for the strain displacement relation. So using that relation, I am going to write the formula for the lateral strains, that is epsilon yy. So epsilon yy is given by 1 by sigma yy minus sigma xx plus sigma zz. Sigma y, we are assuming only normal stress, that is sigma xx. So these two terms will cancel out, and if it cancel out, the only term that is left is sigma xx, and it is given by nu times y by r. So epsilon yy is nu times y by r, and it is same as epsilon zz. Okay, so this is the formula for lateral strain. Using this formula, we can calculate the value of the lateral strain as per the question. The next question, these all formulas are the formula based on the pure bending case, and in the case of bending, when there is shear also present, when there is shear stress also present, or there is a variation in shear stress also, so in that case we have the same formula but in a different way. So in case of bending of beams, we have different formula in the same way, that is we can write out the first, that is the variation of sigma xx. So sigma xx here is given by, it is also vary in x, y and z direction, which is given by minus m of x y upon I z z. So this is the value of sigma xx. Next is the variation of shear stress. So variation of, so this is the formula for variation of normal stress. Next I am writing variation of shear stress, which is given by tau xy of x comma y, which is equal to v of x q of y upon izz into by. So suppose, so this is the variation of shear stress. Variation of shear stress due to bending of beams. Here Vx is the shear force. Izz you already know the shear second moment of area. By is the width of the cross section, width of the shaded region, and qy is the first moment of shaded region. Okay, so suppose we have a cross section. Suppose we have a cross section and this is our neutral axis, and in this region we have to find the variation of shear stress, which is at a distance of y. So basically what we need to find a variation of shear stress, that is tau xy in this shaded region. So we have to find the shear force which is acting on this cross section. Next is the qy, that is the first moment of area, which is given by area of the shaded region times centroid of the shaded region. So the centroidal distance of the shaded region and the area of the shaded region. So in the qy terms, we have two terms, area of the shaded region times y bar, that is variation of the centroid of the shaded region from the neutral axis, and b is the variation of width, that is width of the cross section where we have to find the shear force, and izz is the second moment of area for the cross section, which is about z axis. So in this way we can find the variation of shear stress of any cross section. So these two formula, that is this one and this one, will be used many more time while solving the question. So this all about the first two lectures, and in the third lecture we discussed about the bending of unsymmetrical beams. So we can you can see the lectures and see that how it can be deal unlike the case of a symmetrical beams. So in this case, we have a formula for finding out the moment in moment variation, and the formula we have the shear stress distribution, that is normal stress distribution across the cross section. So we have a formula which is already written in which is already covered in the lectures. So you can go to the lecture and see the derivation. So in that lecture also shear stress distribution in thin and open cross section was covered. So I am just show you the main result that is obtained after derivation for the thin cross section, thin open cross section. So formula for shear stress distribution in thin and open cross section. In thin and open cross section. So shear stress is given by tau xx. Suppose we have an open cross section. We have open cross section, and the S is our variation of arc length, and Z is our the plane. Basically, Z is the plane, and S is the direction. So here we have tau xx in terms of x and s. So this denote S denote direction and x denote plane. So here the tau xx formula is given by this equation, minus 1 by Ts, that is thickness of the cross section, Iyz square minus Iyy Izz times minus Vy Qys Iyy minus Qzs Iyz plus Vz Qys Izz minus Qzs Izz. So this is the formula for CL stress distribution. And if we consider the special case, if y and z axis, if y and z axis are aligned, if y and z axis are aligned along the principal axis, I y z vanishes. That is the mixed moment of inertia vanishes. So here we are assuming y and z axis are aligned along the principal axis. So in that case, we have a simplified formula, that is tau x equal to 1 by Iyy Izz Ts minus Vy Qys Iyy minus Vz Qzs Izz. On simplifying this, we will get Vy Qys upon Vy Qys minus Izz Ts minus Vz Qzs upon Iyy Ts. Okay, so this is the formula for simplified tau xx when we have y and z axis are aligned along the principal axis. Okay, so this is all about the last lectures. So I have briefly give the overview of the 3 lectures which is covered under week 9. So let's start now the problem solving session, which is actually the main goal of this session. Here we will solve some more interesting problem through which you can better understand the concepts which is already covered in these lectures. So let's start with the problem 1. That is our first problem. Problem 1. So I'm writing the question first. For an I beam, for an I section beam, for an I section beam, the beam is subjected to transverse load. Assume the beam is subjected to transverse load. Okay, so we have 3 questions based on this part. So obtain, the first part of this question is obtain an expression for variation in shear stress tau xy within its cross section. You can use the formula. And the second part of this question is using the expression above, draw a graph depicting qualitative variation in shear stress within the cross section. Within the cross section. And the third part of the question is, where is the shear stress maximum? Where is the shear stress maximum? Where is the shear stress maximum? Also, find the ratio. Find the ratio of maximum shear stress to average shear stress in the cross section. In the cross section. So here we have a question. I am repeating once again. The question is, for an I section beam, assume the beam is subjected to transverse load. So we have a beam and the beam is subjected to transverse load. Obtain an expression for for variation in shear stress tau xy within its cross section. So the first question is, we have to find the expression of shear stress variation tau xy within its cross section. The second part of the question says, using the expression above, draw a graph depicting qualitative variation in shear stress within the cross section. And the third part of the question is, where is the shear stress maximum? That is, we have to find the maximum shear stress, then find the ratio of maximum shear stress to average shear stress in the cross section. Then the question is to find the average, that is the ratio of average shear and the maximum shear in the cross section. So let's start this question, solution of this question. So first we have to find the variation of shear stress. So first I will draw an I section. In I section we have two different parts. This part is referred as flange and this part is referred as web. Okay, this is also referred as flange. Suppose we have the thickness of this part is T. This is also symmetric, so this is also T. The width of the cross section is B and we have the neutral axis here. And this length is L by L. This length is also L. Okay. So this is all about the geometry of the cross section. Now we have to find the variation of shear stress. So for the variation of shear stress, so basically tau xy in terms of xy, it is given by Vx qy upon izz into ty. So here we have to find two different things. That is, the first one is qy. We have to find qy is what. Then we have to find izz is what. Ty we already know. So we have to find these three things. So let's start with Izz first. So the second moment of area, calculating second moment of area. So second moment of area is basically IZZ. So here we can see that this is not a uniform cross section. So we have two different parts. The first part is flange and the second part is web. So we have to find out individually the moment of area about neutral axis, second moment of area about neutral axis, and then we have to sum to find out the total second moment of inertia of this cross section. Okay, so let's start to find the second moment of area of the flange. So IZZ for the flange. So IZZT means for the flange. So this one. So we have to find the first the moment of area about neutral axis of this flange. So suppose we have this geometry and we have to find the shear stress distribution on this part. Okay, on this shaded part we have to find the shear stress distribution, and suppose it is at a distance of y. It is distance of y. So the shear stress formula is given by and this length is basically t by 2. So we know if we want to find the second moment of area about this axis, so it's directly becomes 1 by 12 bt cube. Okay, but we have to find the second moment of area about this axis, about this neutral axis. So we have to apply the parallel axis theorem to find out the second moment of area about this axis. So the parallel axis theorem, according to parallel axis theorem, we will know about this axis. Suppose this axis we know that and name it as axis 1. So I of the flange of xx1 plus a times area of the shaded region, area times x bar square, or we say y bar square, which is nothing but this becomes 1 by 12 bt cube plus area of this flange is b into t, and what is y bar is the basically distance of centroidal distance of the flange from the neutral axis. So this length is L, this length is L, and this is t by 2. So it becomes L plus t by 2, L plus t by 2 ka whole square. So this is the second moment of inertia for the flange. Next, for the web. So second moment of second moment of area for the web. So it is given by for the full web. So this is our web. This is our web, and we have to find the IZZ about this neutral axis. So it directly becomes 1 by 12 into t times 2L ka whole cube. 1 by 12 t 2L whole cube, which becomes 8t L cube upon 12. Okay. Now the final second moment of area about neutral axis is given by, because we have two flange, so it becomes 2 times IZZ of the flange plus IZZ of the web. And if we sum over this, we can find the total second moment of area about z axis, about neutral axis. So it becomes 2 times, that is 2 by 12 bt cube plus 2 bt l plus t by 2 whole square plus 8 tl cube upon 12. So this is the final second moment of inertia for okay. So I hope I think there is some connectivity issue. So sorry for the delay. So yeah, we have okay. So this is the final expression for the epsilon izz. Okay, the second moment of area. Next, we have to find the second moment of that is the first moment of the qzz. Okay, we have to find the qy, that is this one. So for this, we have to find individually, first for the flange and the second for the web. So first consider the flange. First consider the flange. First consider the flange. So here qy, we have to find the value of qy. So qy is given by the area of the shaded region. So this is our flange. So this is our flange, and we have to find the area of the shaded region. Okay. So the area is b into b times t plus l, that is t plus l, t plus l minus of y. See here, t plus l minus of y. So it gives us the area of the shaded region. Okay. So qy is b times t plus l minus y times the centroidal distance from the neutral axis. So this is our centroidal distance. So this is the point, and we have to find the centroidal. So if we take this distance, so this is nothing but l t plus l minus y, and if we take the half, we can find out the value of the centroidal distance from this position, and if we add plus y, then we can find out the value of the centroidal distance from this neutral axis. Okay, so it is given by y plus t plus l minus y upon 2, which is nothing but b by 2 t plus l minus y t plus l plus y. Okay, if we finally solve it, b by 2 t plus l whole square minus y square. So this is the expression for flange. So in this case, the shear stress distribution is given by tau yx due to flange is given by vx into this qy, which is nothing but b by 2 upon 2 times b by 2 izz into b, width of the cross section, times t plus l whole square minus y square. So this is the expression for shear stress due to the flange. Now consider the web. Now consider the web. So for web, Qy is given by the area. So in that case, I am assuming that we have to find, suppose we have to find the shear stress distribution. Yes. So we have to find the shear stress distribution of this cross section. Okay. So the complete this one and this one. So we have to find the shear stress distribution about neutral axis for the web. So first we find out this for this cross section. Okay. So for this cross section, it is given by bt b into t into l plus t by 2 plus this cross section, this one. So for this we know that, so this distance is nothing but t, area is given by area equal to t times this distance, which is l plus y by 2, which is l minus y, t times l minus y. So this is our l and this is the distance. Suppose this distance is so it becomes t times l minus y. Okay, area is given by t times l minus y. Now the distance of the centroid of the cross section from the neutral axis, so it is given by half of l minus y plus y. Okay, and if we calculate this, we find out bt times l plus t by 2 plus t times l minus y times half of l plus y. So it finally becomes bt times l plus t by 2 plus t times l minus t by 2, l minus y, l plus y, that is l square minus y square. So this is the final expression for Qy for the web. So shear stress due to web is given by Vx times Qy, that is Bt l plus t by 2 plus t by 2 into l square minus y square upon izz into width. So here width is given by width of the flange is t. So this is the shear stress distribution on the web. So this is all about question number first. Obtain an expression for variation in shear stress tau xy within its cross section. So we have found the variation of shear stress within its cross section. Now the next question is, using the expression above, draw a graph depicting the qualitative variation in shear stress within the cross section. So we have to find the variation of shear stress also. So let's draw then. So suppose we have this cross section, and we have to find the shear stress distribution. So this is our, this is T, and this is, sorry, this is L, this is L, this is also L, and this is T. So we have to find the shear stress variation. So the variation of shear stress is given by So this is the variation of shear stress. In the I cross section. Okay, when you plot, when you do the manipulation, tau xx y at t equal to 0, then at y equal to 0, then at y equal to L, then at y equal to L plus t, you can find out the value of the shear stress. Okay, so this is the final variation of the shear stress. Now the next question. So we have also the third part of this question, that is, where is the shear stress maximum? So you can see from this figure that shear stress is maximum at the center, that is at the neutral axis. Shear stress is maximum at the neutral axis. So we can write here that this is a C part question, this is on B. So shear stress is maximum at the neutral axis. Shear stress is maximum at the neutral axis. And the next part of this question is, find the ratio of maximum shear stress to average shear stress. So basically, average shear stress is given by maximum shear stress, that is Vx upon area of the cross section. Okay, so this is the maximum shear stress. Vx upon area of the cross section. And to find out the average shear stress, we basically use that concept. So tau xy and tau ix due to wave and the flange, and if we take the ratio of this, we can find out the maximum shear stress, ratio of average to maximum shear stress. So this is all about question number first, that is our problem 1. Now then move to the next question, that is problem number 4. Okay, so this is our next question, that is problem number 2. Please ask if you have any doubt on in this question. I think you all have understood this question very well. This is a very good question based on the pure bending of beam. Now the next question is also based on the bending of beam. So the question is, think of a composite beam. Think of a composite beam having rectangular cross section. Having rectangular cross section such that think of a composite beam having rectangular cross section such that one half of the cross section having a square shape is aluminium while the other half is steel. When such a beam is bent, when such a beam is bent, where will be the neutral axis? Where will the neutral axis lie in the cross section? Where will the neutral axis lie in the cross section? And we have to calculate it from the bottom of the cross section. Calculate from the bottom line of cross section. Okay, so I am repeating the question one more time. The question is, think of a composite beam having rectangular cross section such that one half of the cross section having a square shape is aluminium while the other half is steel. When such a beam is bent, where will be the neutral axis lie in the cross section? Calculate from the bottom line of the cross section. Okay, so let's start. So first I will draw the figure for this question. So we have a composite beam. The first half is made of aluminium. And the second half is made of steel. And it is mentioned in the question that aluminium Young's modulus is less than steel Young's modulus. And suppose the width of the beam is h and height of the beam is 2h. So this is a question, and we have to find the where will be the neutral axis lie in the cross section for, yes, so we have to find the location of the neutral axis from the bottom line of the cross section. So from this is our reference line. Okay, so I'm drawing the same figure here. So actually this is a example of composite beam. So obviously their neutral axis doesn't lie on the centroid of the cross section. Okay, so we have somewhere else the neutral axis here in this problem is somewhere else, that is not along the centroid, that is along this line. So it is somewhere else. So we are assuming that it is along this line. We are assuming here that it is along this line. This is our neutral axis line. Okay, so and it is suppose a distance a unit, it is at a distance of a, and we know that from the bending of beams theory that the shear stress is maximum at the two ends and it is zero at the centroid of the cross section. Okay, at the neutral axis. So for this, if we consider this as a complete beam, if we consider this a composite beam as a complete beam, then the bending profile will be this type. The bending profile will be of this type if we consider this as a single beam. Okay, and if for the steel, if we consider only the steel as an individual beam, if we consider this steel as a individual beam, then the final axis will be of this like, then the final bending variation is given by this way. Okay, the final variation is given by this way. And the variation of aluminium, suppose we have only aluminium, so the variation is given by this way. Okay, So here also epsilon xx is minus y by r, and here also epsilon xx is minus y by r, and the resultant of this, the second figure, is actually basically the first one. So it obeys the following formula: epsilon xx is given by minus y by r, where y is the distance from the neutral axis. Distance from neutral axis. So this is our neutral axis, and from here it is distance y. Here the bending stress profile will be discontinuous at the location where the material changes. So there is a material change here, this line, on this line there is a material change. So that's why there is a property change, that is the bending stress profile is discontinuous at this location. So at the position where the material changes, bending stress profile will be different. Bending stress profile will be different. Bending stress profile will be different. Okay, and it is given by this formula, that is sigma xx is nothing but E times epsilon xx, which is also equal to sigma xx of steel is given by minus E of the steel y by r, and it follows from minus h minus a to a. Y is from minus h by a to a. Similarly, sigma ss of aluminium is minus ea, that is Young's modulus of aluminium, times y by r, and it follows from a to h plus a. Okay, and here the main problem of this question is to find the location of the neutral axis. So it is a case of pure bending, we know that already, and here we have only one unknown, that is the a, that is the location of the neutral axis from the centroid of the cross section. So we use the fact here that the total axial force must vanish at the cross section. Okay, so the total axial force must vanish in the cross section due to pure bending. So due to pure bending, the cross section does not exhibit any axial force. So we are using that concept, that is total axial force due to pure bending total axial force total axial force must vanish in the cross section. That is surface integral of area of steel, sigma xx of steel into dA, plus surface integral over area of aluminium, sigma xx of aluminium into dA equal to 0. And here we know the value of the sigma xx due to aluminium and steel. So I directly put here those formula here: minus es upon r, minus h minus a to a, y dy, area is given by y dy, plus minus ea upon r, integral over a to h plus a, y dy equal to 0. So it finally becomes, if we divide both the terms by both the sides from ES, so it finally becomes minus a square minus h minus a whole square plus EA upon ES h plus a का whole square minus a square equal to 0, which finally becomes minus h square 1 minus EA upon ES minus h square 1 minus EA upon ES plus 2HA 1 plus EA upon ES 1 plus EA upon ES equal to 0. Okay, so it finally gives us the value of A, which is given by A equal to h by 2 ES minus EA upon ES plus EA. So this finally gives us the value of A. And in the question we have to find the calculate from the bottom line of the cross section. So this is our bottom line and this is H. Okay, this is H and somewhere here it is H, sorry. And somewhere here it is H, and we have to find the location of neutral axis from this place, and we have to find the location of the neutral axis from this place, that is the bottom line of the cross section. So it is given by H minus A. So the position of neutral axis from bottom line of cross section is equal to H minus H by 2 ES minus EA upon ES plus EA. Okay, so this is the final location of the neutral axis. So this is the problem number 2. So here we have to find the location of neutral axis, given that we have a composite beam made of aluminum and steel, and we are using the concept here that at the cross section, when it is a case of pure bending, axial force must be vanished, and using that equilibrium condition we can find out the location of the neutral axis, which is here unknown is A. So this is problem number 2. Now move on to the next problem, that is problem number 3. This is also based on the bending of beam problem. Problem 3. Okay, a beam of composite, the question is a beam of composite cross section. A beam of composite cross section is subjected to, so till now we have solved 2 questions. The first question is based on the shear stress distribution, and the second question is based on the bending of beams. So this question is also based on the bending of beam, and the question is a beam of composite cross section is subjected to bending moment M, is subjected to bending moment M Z equal to 30 kilonewton. So the question is to find, we have 3 parts in this question. Find the curvature induced in the beam. Find the curvature curvature induced in the beam. The next part of this question is maximum bending stress in wood. Maximum bending stress in wood. And the third part of this question is maximum bending stress in steel. Maximum bending stress in steel. So we have one figure also in this question. I am drawing this figure. So this is a cross section of the composite beam. So these two parts are steel and these two parts are the wood. Okay, and the dimension of this cross section is also given here. So I am writing the dimension. This is 60 mm. This length is 90 mm. This length is again 60 mm. This length is this length is 120 mm. This length is 6 mm. This is also 6 mm. Here the Young's modulus of the steel and wood is also given. So Young's modulus of steel is considered here 200 gigapascal, and the Young's modulus of wood is given here 10 gigapascal. Okay, and the axis here is, this is along y direction and this is along z direction. And in between of this wooden structure there is no material. It is empty space, or we say void. There is empty space. There is no material present in this system. So here we have to find the curvature induced in the beam. So to find out the curvature induced in the beam, we first find the bending stiffness of the cross section. So here we see that it is a case of symmetrical beam. There is no unsymmetry present in this cross section. So we can simply find out the bending stiffness of the whole cross section. So bending stiffness of the cross section is, so total bending stiffness of the cross section is EI total. So we have two material here, steel and wood. So we have to find the steel bending stiffness. So here you have the steel E and I here both are from the steel cross section, and EI of the wood. So E of the steel is already mentioned here in the question, E of S, and I of the steel. So it is a rectangular cross section. So we simply use that formula, that is 1 by 12 VH cube. So here the width of the steel cross section is 0.06 mm, that is 6 mm. So we simply write 6 into H cube. So what is the height here? 90, 60 and 60, that is coming out to be 210 mm. Yes, 210 cube plus I of the wood. So E of the wood is given here, EW times I of the wood. So here you see that there is some empty space available in the cross section. That is, there is no material in between these two wooden cross section. So we have to find, first assuming that the cross section is completely filled with wooden material. So in that case, what is the second moment of area? So it is given by 1 by 12 into width. Here width of the wooden cross section is 120 mm. So 120 into height. What is the height here? Same, that is 210 mm. So 1 by 12, 120 into 210 cube. Why? Because I am assuming that the empty space is also filled with wooden material. Now, because I am assuming that the empty space is filled with the wooden material, so we have to subtract the second moment of area of this this empty space also, because the first I have considered this, so we have to subtract it also, because in that place there is no material, that is empty. So 1 by 12 into width of that empty space is 120 into what is the height here? So 90 cube. So this is the final bending stiffness of the cross section. So I am just calculating it. What is the EW here? ES here. ES is 200 gigapascal, which is basically 200 times 10 to the power 3 megapascal. So I am keeping all the units in Newton per mm square. So 1 megapascal is 1 Newton per mm square. Okay. So in megapascal it is given as 200 times 10 to the power 3 times 1 by 12 into 6 into 210 cube, plus EW is given as 10 gigapascal, which is nothing but 10 into 10 to the power 3 megapascal, that is 10 into 10 to the power 4 Newton per mm square, times 1 by 12 120 into 210 cube minus 1 by 12 120 into 90 cube. So I'm calculating this using calculator. So you can also calculate and tell me the answer. So here 200 into 6 into 210 cube divided by 12, so it is given as 9.261 into 10 to the power 11 plus 120 times 210 cube minus 120 times 90 cube divided by 12, plus 8.532 into 10 to the power 11. So it finally becomes 8.532 plus 9.261, that is 17.793 into 10 to the power 11. And what is the unit here? Newton per mm square into mm to the power 4. So it is Newton mm square. Now move to the next question. So we have found the value of total bending stiffness of the cross section. Now the first part of the question is to calculate the curvature induced in the beam. So the curvature induced in the beam is kappa is equal to mz upon EI total, and mz is already given the question, I guess. Yes, 30 kilonewton. So 30 into 10 to the power 3 upon 17.793 into 10 to the power 11. So it finally becomes 30 divided by 17.793 is 1.686 into 10 to the power minus 8. Okay, so this is the question here. First part of the question is completed now. Now the second part of the question is maximum bending stress in wood. Maximum bending stress in wood. So maximum bending stress in wood is given by sigma s, because we know that the maximum bending stress is occur at the two extreme points, that is at the top or at the bottom, but in opposite direction, and it is zero in the neutral axis, at the neutral axis. So basically we have to find the maximum bending stress at the top. Bending stress at the top, so it is given by Es into kappa times y, that is the position of the point, that is position of the cross section from the neutral axis. So this is our neutral axis, sorry, suppose this is our neutral axis. So this point is given by 45. What is the length of this line? 45 plus 60, that is 125 mm. So simply write it in meter. So Es into kappa 0.045 plus 0.06 Newton per meter square. Okay. The third part of the question is maximum bending stress in steel. So in the same way, we can find out the maximum bending stress in steel. Maximum bending stress in steel is sigma. So this is the maximum bending stress in steel, and here, sorry, I have written wrong here. So maximum bending stress in steel, and this is maximum bending stress in wood. So it is given by sigma wood at the top, which is nothing but EW, that is Young's modulus of the wood, times kappa curvature, and it is again the same thing, 0.05 plus 0.06 Newton per mm per meter square. Why it is Newton per meter square? Because I have written here the units of position, that is the y position in meter. That's why it is the unit here finally written in Newton per meter square. So this is all about question number 3. Now move forward to the next question, that is problem number 4. Problem 4. So this problem is also based on the bending of beams. So I will write the question. So follow this question. A flat steel bar, a flat steel bar, a flat steel bar 1 inch wide, 1 inch wide by 0.25 inch thick and 40-inch long is bent by couples applied at the ends, is bent by couples applied at the ends, applied at the ends, so that the midpoint deflection is 1 inch, so that the midpoint deflection is 1 inch. Okay, compute the question is compute the stress in the bar, compute the stress in the bar and the magnitude of the applied couples, and the magnitude of the applied couples. Okay, here you can use Young's modulus as 200 gigapascal. Okay, so there is a figure also in this question. I am drawing it. So first we have a beam, a flat steel bar, and from the ends we are applying end couple. Okay, of M. So we have cross section. The dimension of cross section is, this is of 1 inch and this is of 1 by 4 inch. Okay, and this is angle theta, and this distance is rho, this is also rho. The length of this bar is 20 inch and this is also 20 inch. So the question is, I am repeating the question one more time. A flat steel bar which is of 1 inch wide by 0.25 inch thick and 40 inch long. Okay, so we have a steel bar which is of 40 inch long, is bent by couple applied at the ends so that the midpoint deflection is 1 inch. So it is actually bent in this way. So it bent by 1 inch. Okay, so it bent by 1 inch. Compute the stress in the bar and the magnitude of the applied couple. So we have to find the value of M, what is the magnitude of M, and the stress value, stress in the bar. So whenever we applied, suppose we have a beam here and we apply a end load, end moment. So whenever we applied end moment, the beam bends. In actually the straight beam becomes curved, and due to this, actually, for in the case of pure bending, that is in the case of bending deformation, actually the length of the beam will remain the same. However, to maintain the length same, the end point will also shift downward, because suppose this is a straight beam and if we bend, so it actually bend, and to remain and to maintain the length of the beam to be same, the end point also fixed, also move downward. But here, as the deflection is very small, that is 1 inch, so we are assuming that the deformed beam will be of the same length. So here we see that so here we assume that the two ends, that this two ends, sorry, these two ends, these two ends, sorry, yes, these two ends they remains here even after the deformation, that is after the bending happen. So we are just using the geometry, using the geometry condition. So suppose this is our geometry condition. So this is, we know the rho, the value of the rho, and here due to bending, that rho becomes actually rho minus 1 inch. And what is the value of this? This is L by 2. This is nothing but 20 inch. Okay. And we are using here the Pythagoras theorem, that is rho minus 1 inch whole square plus L square by 4. So I'm directly writing here, suppose this is delta, and we know the value of delta, that is 1 inch. So using Pythagoras theorem, rho minus delta whole square plus L square by 4, that is L by 2 square, L by 2 whole square equal to rho square. Rho square minus, it becomes rho square minus 2 rho delta plus delta square equal to plus L square by 4 equal to rho square, or we say rho square, rho equal to L square plus 4 delta square upon 8 delta. And if we put the value, that is L is 20 square plus 4 times 1 square upon 8, that is 404 upon 8, no, 8 into delta, right? So L is what? L here is L by 2 is basically 20 inch. Yes. What is L? So L here is 20, that is 440. L is here 40. 40 square plus 4 times 1 square upon 8. 1600 plus 4 upon 8, which is coming out to be 200.5 inch. Okay. So from here we calculate the value of rho, that is 200.5 inch. And the question is to calculate the value of bending couple required to make a deflection of 1 inch. So moment bending couple, that is M, is given by EI kappa, or we say EI by radius of curvature, and the radius of curvature here is rho. And what is the value of E here? 29. So first we have to convert the gigapascal into lb per inch square, that is pound per inch square. So I am writing the conversion here. 1 lb per inch square equal to 0.00689476 Newton per mm square. So when you calculate, when using this conversion in calculating the value of bending moment, so it comes out to be 188.3 lb inch. Okay, and here I is given by 1 by 12 into BHQ. And what is the B width of the cross section? That is 1 inch. Sorry. And H is 1 by 4 inch cube. So we simply put the value of I here, rho. So we simply put the value of I here, rho already we know from that the above this one, and E we know the value of Young's modulus. It is already mentioned in the question. The one thing that you please consider here is that before going any calculation, before going through any calculation, you must see that the unit that is the unit we are using for the value is the same on all the cases. So first we have to convert all the unit in the same place. That is, if you are using in lb per inch square, so you are using lb per inch square for every dimension. If you are using Newton per mm square, then you are using Newton per mm square for every variables. Okay, so this is question number 4. So problem 4 is about to calculate the magnitude of applied moment. Okay. Here also we have to find one question more here. We have to find the stress, that is the bending stress. The bending stress is given by my upon I. Okay. In the starting of this session, I have written down the formula for the bending in case of pure bending of beams. So you can see here also in the first example. Yes. So it is given by minus Ey upon R, and y is the centroidal distance. So here the bending stress is given by my by R, or we say minus Ey by R. And what is E here? E is basically, you can find out here, y is basically the half of 1 by 4 inch. That is the location of the topmost point from the neutral axis upon R. And what is R here? R we can also 1 by R as rho, and we can find the rho here value. So using this formula you can find the value of bending stress. So we have two questions asked here. The first question is to find the bending moment, and the second question is to find the bending stress. So we found both the values here. Now come on to the next question, that is problem 5. So this is problem 4. Now problem 5 is, in a laboratory test of a beam loaded by end couples the longitudinal fibers at layer AB in the figure below are found to increase 60 by 10 to the power minus 3 mm, whereas those at CD decrease can decrease 100 times 10 to the power minus 3 mm in the 200 mm gauge length. 200 mm gauge length. Using Young's modulus as 270 gigapascal, using E as 70 gigapascal, determine the flexural stress. Determine the flexural stress in the top and bottom fibers. In the top and bottom fibers. Okay. So we have a figure also in this question. I am drawing that figure. Okay. So this is a figure. I am repeating the question once again. In a laboratory test of beam loaded by end couples, the longitudinal fibers at layer AB in the figure below are found to increase 60 cross 60 means 60 times 10 to the power minus 3 mm, whereas those at CD decreases by 100 times 10 to the power minus 3 mm in the 200 mm gauge length. Using E is equal to, that is Young's modulus is given here, that is 70 gigapascal. Determine the flexural stress. Flexural stress is nothing but bending stress. We also call bending stress as flexural stress. So bending stress, determine the flexural stress in the top and the bottom fibers. Okay, so let's do it. So here the beam is given here, the exact beam given here, but there is no mention about the cross section, whether it is symmetrical or not. So we are here assuming that the cross section is not symmetrical here, and that's why the neutral axis is not passes through the centroid of the cross section. Okay, so we are assuming here that the neutral axis is not passes through the centroid of the cross section. So we are here assuming that neutral axis lies somewhere here. Okay. So the variation of so we are assuming that the neutral axis is lying somewhere here and it is at a distance x from the AB line. So suppose this distance is at x, this distance is x, so this distance becomes x plus 30 and this distance is 120, so it will become 120 minus x and this will become 195 minus x if we are assuming this is our neutral axis. And here it is mentioned that this delta is equal to 60 into 10 to the power minus, that is the elongation. It increases by 60 into 10 to the power minus 3 mm and it decreases by 100 times 10 to the power minus 3 mm. So this is delta at bottom and this is delta at top. Okay, so we know that epsilon xx equal to minus y upon r. Epsilon xx is equal to minus y upon r, and here in the pure bending of beams, radius of curvature is constant. So the ratio y upon epsilon xx must also be a constant. Okay. So from this we can say that, so here it is mentioned in the question that AB line increases, longitudinal fiber AB increases by 60 into 10 to the power minus 3 mm and the CD decreases by 100 into 10 to the power minus 3 mm. And we know that from the strain displacement relation, that is a longitudinal strain due to bending is given by minus y by r, and here r is fixed, that is constant here, so the ratio y by epsilon xx must also be a constant. So we are using that condition for this case, for this two case where one the top fiber is in extension and the lower fiber, that is a bottom fiber, is in compression. So using that concept, the ratio y by epsilon xx must be a constant. So x by epsilon AB, because here this distance is x, so x by epsilon AB is equal to x minus 120 upon epsilon CD. And what is epsilon AB here? It is already given in the question. Epsilon AB is plus 60 into 10 to the power minus 3. 60 into 10 to the power. So what is epsilon? Delta L upon L, that is change in length. So in the first fiber AB, the length is increases by 16 to 10 to the power minus 3 mm. So delta L is 16 to 10 to the power minus 3 mm upon L. What is the original length of the fiber is 200 mm. It's already mentioned in the question. Now x minus 120. What is epsilon CD? So epsilon CD is given by delta L upon L, where delta L is the change in length of the fiber CD. and it is in the length of the fiber actually decreases by 100 into 10 to the power minus 3, so therefore it is minus of 100 into 10 to the power minus 3 upon 200. So it finally becomes x equal to 0.6 into 120 minus x. Okay, so x equal to equal to 0.6 into 120 minus 0.6x. So 0.7x equal to 70. Sorry, I'm doing one mistake here. Yes. So x plus 0.6x equal to 72. That is 1.6x equal to 72. X equal to 720 upon 60. 16 for the 64. That is 45 mm. So x equal to 45 mm. So we know the position of the neutral axis, that is 45 mm, 45 mm from the 45 mm from the AB fiber. Okay, we know the position of the neutral axis. Now what is the question here? We have to find the flexural stress, that is bending stress in top and bottom fiber. So bending stress in top fiber and bottom fiber. So bending stress. So first we have to find the value of the strain in the top and the bottom fiber. So we are using the same concept, that is the ratio, that is the radius of curvature is same in this case. So x upon, so for top fiber, x upon epsilon AB is equal to x plus 30 upon epsilon top, because here we see that in the figure that from the neutral axis the position of the top fiber is x plus 30. So epsilon of top is given by x plus 30 upon x into epsilon AB. Okay, and what is x is given here? 45, and 45 plus 30 is 75 upon x is 45 into epsilon AB 60 into 10 to the power minus 3 upon 200. So so it's coming out to be 5 into 10 to the power minus 4. So epsilon root of fiber is 5 into 10 to the power minus 4. Okay, so the bending stress in the top fiber is equal to, is sigma on the top fiber is E into epsilon on the top fiber, that is 70 into gigapascal, so 70 into 10 to the power 9 into 5 into 10 to the power minus 4, that is 35 megapascal. If you convert it in megapascal, so yeah, so 35 megapascal. So sigma on the top fiber is 35 megapascal. Okay, now for bottom fiber, we are using the same concept, that is the ratio of x upon epsilon should be same. So x upon epsilon AB equal to 195 minus x, 195 minus x, sorry, so it is nothing but x upon epsilon AB is minus of, so this distance is x, right? and this is 195 minus x, and this is in downward direction. So yeah, x minus 195 upon epsilon of bottom fiber, and epsilon of bottom fiber is epsilon AB into x minus 195 upon x. Epsilon AB is given the question already, 60 into 10 to the power minus 3 minus 45 195 150 upon x. What is x? 45. That is minus 20 into 10 to the power minus 2. It's coming out to be 20 into 10 to the power minus 2. Okay. Now we have to find the bending stress on the bottom fiber. Bending stress on the bottom fiber. So it is given by sigma bottom equal to E times epsilon bottom, which is 70 into 10 to the power 3 into 20 into 10 to the power minus 2. That is 1400 14,000 megapascal, minus 14,000 megapascal. I have done one mistake here. I have to divide by 200 also. Yeah, here epsilon AB. So epsilon AB is 16 to 10 to the power minus 3 upon 200. So upon 200. So it's finally coming out to be minus of 1 into 10 to the power minus 3, or we say 10 into 10 to the power minus of 10 into 10 to the power minus 4. Okay. So it becomes 10 into 10 to the power minus 4. So finally it's coming out to be minus 70 megapascal. Sigma on the bottom. Bending stress at the bottom fiber, minus 70 megapascal. So it is in compression. That's why it's coming out to be negative, minus 70 megapascal. So this is the last question that is solved now. So today we have solved around 5 questions, and these all questions are very important in terms of bending of beams. So I hope you all understand these concepts through this question, and yes, this is all about today's session. And if you have any doubt regarding this question or anything else related to the course, you can reach out to me. You can also write in the chat box in the YouTube channel. I will definitely write there. And if you have any further doubt, you can also ask me in the next coming session, which is scheduled to be on the next Friday. So thanks for joining today. You can now leave the meeting. Bye.